Armed with our set of fluid dynamics equations, we're ready to start perturbing our fluid mediums. And the first one that we're going to do is to produce a small density enhancement, and that will result in a propagation of a sound wave. Now, sound waves are very important in astrophysics as a way of conveying information about, for example, pressure from one place to another. And how quickly that information gets there is set by the sound speed. So this comes about, for example, in the situation where we consider a molecular cloud. The molecular cloud is collapsing under gravity, and there's a time scale set for the gravitational collapse. And that's balanced out. If it's a steady state, that would be balanced out by the pressure of that molecular cloud. And the sound speed is how we'll set how long it takes to establish some form of equilibrium. So we would balance out the pressure against gravity, and the time scales are set by the collapsing time scale or the sound crossing time for that pressure to push against that collapse. So that's just an example. And what we're going to do over the next lecture is to develop the formalism for a sound wave and how that would propagate with fluid equations. And then we'll play around with those as part of our workshops. So let me share my screen and we'll get going. So the mechanism that we're going to put in place here is to allow for a small disturbance to happen in our medium. And from there, we're going to propagate the sound wave. Now, we'll apply a similar mechanism when we start talking about instabilities, where we allow a disturbance to change, and we'll work through that here. In this case, let's consider that we have a fluid in equilibrium. So there's a fluid initially in equilibrium. And that means that the partial derivatives with respect to time of everything are zero. So we have uniform density, pressure, and velocity field is equal to zero. Now we're going to perturb this gently. And that means it's just going to be a small perturbation of the form rho is equal to rho naught plus rho delta rho. And likewise, we have P equals P naught plus delta P. And we're going to put in place a velocity field, which is delta U. These are all Lagrangian changes. And we can set out the relationship between the Lagrangian change. So what I've taken is I've taken my particular volume element of fluid and I've perturbed its density a little bit, increase it just a little bit, increase its pressure just a little bit. Now, how does that relate if I consider the flow as a whole and consider the Eulerian perturbations? Well, the Eulerian, so this part was Lagrangian. The Eulerian perturbations say that the change in density is equal to the change in density of this particular element, plus some vector that describes the displacement dotted with grad of rho naught. And that's the Eulerian situation. Now, we've said in our initial definition that this is a uniform medium, so rho naught must be constant. It's totally uniform. Therefore, the gradient of rho naught is going to go to zero. So I'm going to get rid of this term, and that becomes zero. And so then from there, we can then start to write out how do these change with time. So the change in time, the partial derivative of rho naught plus delta rho plus the divergence of the term rho naught plus grad rho. So I'm just filling this into the continuity equation. Is equal to 0. So all of that comes about from the continuity equation. So I've replaced the normal terms in the continuity equation with my perturbed terms. And then I want to consider only first order terms because this is a small perturbance and I don't care about the second order terms. So I'm going to expand this equation so that I have the partial derivative of rho naught with respect to time, which is of course going to go to 0, partial derivative of delta rho plus grad rho naught delta u plus grad delta rho dot grad u plus rho naught grad, just make certain I don't replicate the terms, there we are, grad dot, so that's a divergence, rho naught divergence, the gradient of u plus delta rho dot delta u is equal to 0. So I've expanded out all of those terms. And now I'm going to get rid of things that shouldn't be changing because they're either constant with time or they're second order terms. And so that means I can get rid of that one because it's a uniform field. So that goes to 0. That means I can get rid of this one, which also goes to 0 because it's a uniform field. I can get rid of this one, which is a second order term. And I can get rid of this one, which is also a second order term. And the end result that comes out from all of that is that we have partial derivative with respect to time squared dt, oops, wrote that incorrectly, sorry, delta t squared is equal to gp d rho grad squared delta rho. And this is a wave equation. It's a standard wave equation, which means that you can write down solutions for that equation that are based off of an exponential term. So it has solutions of the form delta rho equals delta rho naught exponential of I k dot x if omega t. Standard wave equation, or in one dimension, you might imagine it just being delta rho is equal to delta rho naught e to the I kx minus omega t. And you can see that that's a wave form. So we can substitute that into the wave equation that we've written out above. And what we find substitute into wave equation. And the end result is omega squared over k squared is equal to dp d rho. A very simple form where omega is, of course, 2 pi nu and k is 2 pi lambda. So omega on k is equal to the speed of propagation of constant phase of this perturbation. Now, if you make the next step and you consider one of our equations of state that we wrote out. For example, we wrote an equation of state, P proportional to rho to the gamma, then we can work through and write out a sound speed for this set of, so the sound speed is the partial derivative of P with respect to rho, the square of the sound speed, because we saw already up here that this was equal to sound speed. And so based off of my equation of state, I can take the partial derivative of, for example, P equals nkt, or P is equal to rho kt over the mass of the proton times the mean molecular weight. And that implies straight away that the sound speed would be equal to the square root of 1 over mu mp kt, where I've taken the derivative of the pressure with respect to density and solved for the sound speed. And for this simple equation of state, then what we find is you can solve that the sound speed is on the order of 0.09 times the temperature in Kelvin to the 1/2 power. So think about that just for a minute. That means that as the temperature gets higher and higher, the sound speed gets higher, but only as the square root of that. So the sound speed in a medium that's 10 million Kelvin is much higher than the sound speed in a molecular cloud, which may be only 10 Kelvin. And so if the sound speed is high in that rarefied medium, then you can propagate information from one side of the medium to the other very quickly. So an example is that the sound speed in the halo of a galaxy, which has got a 10 million or so Kelvin temperature to it, is very fast. It's very quick to transfer information from one place to another, whereas in a molecular cloud, it's very, very slow. So the way that we've actually written this out can allow us to consider perturbations in other forms. And one thing that we might want to write down is that the change in the velocity is just the change in the density, initial density, over the initial density times rho on k, e to the I kx. This follows directly from the wave equation that I've written out before. And that tells us that the change in, this should have been change in initial density, not change in rho naught. Pardon me. Is equal to the sound speed times the change in density over the initial density. In general, we can solve wave equations like what we just did for all perturbations. And you follow the same method that we used, and that is as follows. We first use Euler's equation. And the other forms of the fluid equations. You describe an equilibrium. So in our case, that was just rho naught, and that's the equilibrium, and there's no change in time initially. You choose a perturbed delta values. And those are Lagrangian. You convert to delta, meaning the Eulerian delta, using a small perturbation vector. You cancel out the second order terms. And you're left with a wave equation that can be dealt with. So that means that instead of perturbing just simply a density, I could have perturbed just the pressure, or I could perturb a velocity, and I can solve for those wave equations in all ways. So let me just write one final thing, which is to think about the sound speed in a general sense, because sound speeds are something that you're going to want to derive in many cases. So the sound speed, consider temperature of 10 to the 4 Kelvin, and it's warm atomic medium. So we're going to write down that the sound speed is about 9 kilometers a second, and in parsecs per million years, that comes about, of course, because we had times the square root of t. And you come up with a very handy relationship that 1 kilometer per second is approximately 1 parsec per mega year. And so from that, you can estimate that in a 10 to the 4 Kelvin medium, it would be about sound speed of about 9 parsecs per mega year, which means that a typical cloud has a sound crossing time of order 1 million years. So we'll stop there, and we'll pick up on more perturbations in our following lectures.